We had two bits of homework last night, guys. The first one was worksheet number 1. The second one was a couple practice problems that we had to do out of our textbook. We've got the answers for the first 5 questions for worksheet number 1 up there right now. Just take a peek at them, okay? Don't worry about the solutions. Okay, we're not concerning ourselves with the solutions right now. You don't need to know how I got an answer right now. If you didn't get the answer that's up on the board right now, then we'll go over that question. Okay, we're not going to rely on you just looking at this sheet, okay? So just make a note if you didn't get one of the correct answers, and then we'll take a look at it in just a moment once we've finished looking at all of these. We'll flip the page there, have a look at the last group, 6, 7, and 8 now. Again, same thing. Don't worry about how to do the question if you didn't get it. Just worry about whether you get the right answer or the wrong answer, or whether you struggled or not with the question, and we'll take a look at any that you need help with. All right, any questions on worksheet number 1 to 8? Any of those ones that you'd like to go over? Doesn't mean necessarily that you got the question wrong. Maybe you did get it right. You're like, oh, wow, surprise, I got that one right. If it's one of those questions that you're just not sure exactly why you got it right, or you weren't quite sure exactly how to go about it, but you ended up getting the right answer, then raise your hand anyways for that question, okay, because we want to go over that. Bailey? Okay, we got 5 and 7. Any others? Yeah, 6. We got 5, 6, 7. Any others, guys? 5, 6, 7? All right, that's not so bad. Take a look at a blank copy now of 5, 6, and 7. Let's read the question. You guys have all had a chance to read the question. You did it last night. Everybody did. As a 5-kilogram ball accelerates at a rate of 2 meters per second for 1.5 seconds, what's the ball's momentum after the acceleration? We did a question something like this yesterday as a practice problem, although not exactly like this. Remember, the ball fell, and we wanted to find the momentum as it struck the ground. The big thing that we had to remember in that question is that we wanted the momentum at a specific time, at one moment in time. The momentum is changing in that example that we did yesterday. The momentum is changing in this question as well. We don't want the change in momentum. We don't want the momentum at the beginning or in the middle. We want the momentum specifically at the end of this problem. So, in order to get that, we're going to need the velocity at the end of this problem to go along with that momentum at the end. Let's circle some givens here. That's going to be m. What's this going to be? First time we've seen this term this year. 2 meters per second squared, Tom? Good. That's going to be acceleration. It looks like it's positive. It's speeding up. Yeah. What's this thing right here? Yep. It's time. We're going to call that delta t. We want to find the momentum after the acceleration. Let's call it pf. We know that pf is equal to m times v. Okay? That's really the part of the problem that we're trying to solve here. Right? What's the momentum? But in order to solve this part of the problem, we need to solve another part of the problem as well. That's the acceleration phase. Remember, we had to look at the falling phase yesterday, and then at the end with the collision yesterday. And here we've got the acceleration phase, and then at the end of that acceleration, let's get the momentum. How are we going to get VF there? And we've got M. That's easy enough. It's 5 kilograms. How are we going to get VF in order to plug into that equation to solve for that momentum at the end? Caitlin's looking at her data sheet right there, and I think she's got an answer for me, right? D is equal to VIT plus 1 half AT squared. Okay, there's a number of equations that are valid here. VIT plus 1 half AT squared. That's a perfectly valid equation anytime you're dealing with acceleration. So, although that's not the one we're probably going to use here because it doesn't give us VF, it's okay to try that. Okay, understand. I want you guys to wrap your heads around this, especially in Physics 30 here. If you try a valid equation, you don't need to worry about whether it's the right one or not. Because the worst case scenario, the worst thing that's going to happen to you is that you're going to have to try again. Okay, so Caitlin tries this one. She sees, oh, VIT, AT, perfect. Oh, wait a sec, it gives me D. Right? I want VF. Right? But that's okay, because you didn't get a wrong number for VF. You just didn't get a number for VF, so you try again, right? That's okay. Okay, what you don't want to try here is V equals D over T, because that's not valid here, right? Okay, you want to try something that's valid. If it's the wrong one, don't worry about it. Try again. Okay, got another one, Caitlin? Or should we call on somebody else this time? Oh, okay, interesting. Okay, interesting. So she said she used this one. She got D, and then she ended up doing something else, like VF squared is equal to VI squared plus 2AD maybe? Okay, okay, fair enough. So she got D first, and then she used something like this. Knowing VI, knowing A, and now knowing D. Good, perfect. Good. Again, if you use a valid equation, okay, the worst that's going to happen is you're going to have to try again. Okay? You might end up getting the right thing using that method. That's not the way that I was thinking, but that's perfectly valid, and that'll give you the right answer. Okay? There's nothing wrong with that at all. It's just as good as my way. Anybody suggest one that's maybe a little bit quicker or a little bit more efficient? No better, but just a little bit more efficient? Yeah. Yeah. That's the one that I was thinking. A is equal to delta V over delta T. Okay. Delta V is equal to A times T. And if VI is 0, okay, if VI is 0, then delta V is the same as VF. Get that value for VF. And plug it back into there. Does that make sense? Caitlin, does that make sense how that's a bit quicker? But no better. Okay, no better. Okay, in the end, when you write a unit test or you write a diploma exam, you want to, on average, take a maximum of 3 minutes per question. Okay, my method, okay, was a little bit quicker than your method, but you're still well ahead of 3 minutes there, so you're fine on that. Okay, even if it is 30 extra seconds there. All right, number 6. So a 2-kilogram rock is dropped from the top of a 30-meter high building. What's the ball's momentum at the time that it strikes the ground? This is almost exactly like that example we did yesterday, right? It's almost exactly the same. What do we got here? 2 kilograms is the mass, right? What are we going to say this 30 meters is? Yeah, or displacement we'll call it because it's change in position. It's dropped, so we're going to read between the lines here and say that VI is 0 meters per second if it's dropped. We want to find the momentum as it strikes the ground. We want to find PF. Again, it's M times VF, but we got to get VF. What do you want to do to find VF this time? Think back to that problem yesterday. Yeah. Good. Good. VF squared is equal to VI squared plus 2AD. Hey, that's exactly what I spotted first as well. But just like in the last question, there are other ways to do this equally as valid. Okay? No worse, no better. Okay? And that's okay if you use something different than me. If it's valid, then, and that's the thought that comes to your mind, then go with it. I like that sometimes actually, when somebody does it something a way differently than me, because it shows a little bit more creativity, right? Than just, oh, this is the way Mr. Dickie does it every time. If you can do it a different way, then it means you're thinking about it a little bit more. And that's important, is to be thinking about it, not just regurgitating, right? All right, so we solve for VF there. That's the square root of 2 times A times D. We get, what do we get for VF there? Is it 24.26? And we plug that number back into here, and we get the answer that I had up on the board a few minutes ago, which was 48.5 down, or negative 48.5. 5, 6, and 7 we needed to go over, was it? Or was it 8 as well? It's 5, 6, and 7? Okay. 7. I like this one. I like this one. This one's kind of a trick. It's not so bad, actually. It's just once you kind of catch the trick, but it's kind of tough until you catch that. It says a 1 kilogram rock is thrown up into the air from ground level at a speed of 8 meters per second. The ball travels up to a max height, then returns to the ground. What's the rock's momentum as it strikes the ground? So this seems more complicated than the last question. It's not just falling and we want to find the momentum as it strikes the ground. It's rising and then falling, and then we want to find the momentum as it strikes the ground. So there's more to it, right? Well, funny enough, there's actually less to it than the other question. Here's why. In this question, we still need to find the final momentum, the momentum as it strikes the ground. We need the mass, and we need the final velocity. But if we look closely at this and just give it some thought, we know what the final velocity is already. What is it? I'm thinking right now when I ask you this question, I might get 2 responses. I'm curious to see who's right. What do you think the final velocity is? Yep. Yep. It's 0 when it reaches the top of the arc, but we want to find the momentum when it hits the ground again, right? So not that momentum at the top. You're absolutely right. It's 0 when it reaches the top. And that might help us, depending upon which way you do the question. That might help us. Right? It's 8. Think about it. As if something goes up, at what rate does it slow down when it's going up into the air? What's the rate of deceleration as it goes up into the air? Tom? Negative 9.81. Okay, so it decelerates at 9.81 until it stops. And then what happens? It falls down at 9.81 over the same distance. So if it slows down at 9.81 over a certain distance and speeds up at 9.81 over the same distance, then isn't the final velocity going to be the same as the initial? Isn't it going to be moving at 8 meters per second when it strikes the ground? That's it. Negative 8.0 kilograms meters per second. Done. Does that make sense? Now, Emma said she got that the momentum would be 0, the velocity would be 0 when it reaches the top. If you don't catch this whole thing that we spotted there, that Tom got and that Maria got there, that's okay again. Okay? That's okay. We can still do that question exactly the way that Maria was thinking. It just takes us a little bit more time, that's all. So Maria catches that on the trip up, its final velocity would be 0. Therefore, on the trip down, its initial velocity would be 0, right? Well, if we analyze the trip down, VI would be 0. A would be neg 9.81. Actually, let's, is there a way for us to find the final speed there, the final velocity? Oh, you know what we'd have to do? We'd have to analyze the trip up first. Okay. VI would be 8. VF would be 0. A would be neg 9.81. Let's get displacement. How high does it go up? Okay. And then we could say the displacement is on its trip down is the same as on the trip up. We could find VF. But what would we find for VF? It would be 8 meters per second, right? So it'd be kind of a roundabout way of getting the same thing, but still an equally correct way of doing it. And is that the way you ended up doing it? Okay. Like I say, guys, I don't care if you do it the quickest way or the most efficient way. Okay? I care that you're thinking about it and logically and correctly, and not necessarily the quickest way. The quickest way isn't necessarily the best way. Okay there? All right. We had one more bit of homework as well, and that was page 452, a couple practice problems on variable value changing. So let's take a look at those ones now. If you remember yesterday, I said in question number 1, we had to be really careful of what it said right here. When its mass decreases by a factor of 3/4, its mass becomes what? A quarter, right? 1/4. If it said its mass decreased to 1/4 of what it was, then it's easy. If it decreases by 3/4, then the wording is a little bit tricky. So we got to be careful about that. Really, really tricky. So tricky, in fact, that the people that wrote the textbook did their own question wrong because they assumed that the new mass was 3/4 of what it was, not 1/4 of what it was. All right, let's do question number 1, largely because there is a wrong answer in the answers there. And if we need to go over question number 2, we'll do that as well. Many modern rifles use bullets that have less mass and reach higher speeds than bullets for older rifles, resulting in increased accuracy over longer distances. The momentum of a bullet is 8.25 to the west. What's the momentum if the speed is increased by 3/2 and its mass is decreased by 3/4? So we're changing the value of variables. We're changing the value of the speed and of the mass without knowing what the values were to begin with. Look, if we knew what the values were to begin with, then let's just figure out what the new values are and then do it the old-fashioned way, P equals m times v. Okay, but we don't know what those values are. So let's go through our steps. Let's write down our relevant equation. P is equal to m times v. Put a little subscript beside the P. What subscript do we put there? Doesn't really matter, right? What's the way that we usually do it? We'll call it P. Oh, stands for the old momentum or the original momentum. Before I do anything to it, that's what it is. Its original momentum was also 8.25. We don't know what its new momentum is. Its new momentum is still mass times velocity, but the mass is no longer m. What's the mass now? Devin, what's the mass now? 1/4 m, yeah. Here it was mass times velocity. Here it's still mass times velocity, but mass is 1/4 m instead of m. What's velocity? This one's not a hard one. Bailey, what's velocity now? There we go. 3/2 times v. Now, if you're not good with fractions, this can be a little bit tricky here right now. There's a couple of these that we'll do later on where you have to divide by fractions, which is even more tricky if you're not good with fractions. It's not too bad here, though. Let's pull out the numbers in the front here. 1 times 3 is 3. 4 times 2 is 8. So it becomes 3/8 of m times v. Well, we know what the value of mv is. 8.25. So my new answer becomes 3/8 of 8.25. And of course, technically that would be to the west, right? Because the original momentum was also to the west. Good? How about question number 2? Do we want to do question number 2? Yes? Okay. It's a little bit trickier because it's changing the velocity, right? What does the velocity become? And we haven't done one of those yet. During one part of the liftoff of a model rocket, its momentum increases by a factor of 4, while its mass is halved. The velocity of the rocket was initially 8.5. What's the final velocity during that time interval? Our relevant equation is P is equal to m times v, but since we're trying to find what happens to the velocity, we want to rearrange that. Let's make it v over p, or m over p, or p over m, whatever it is. M times v, p over m. Yes. So that's my relevant equation now. It's just a rearranged form of it, right? My old velocity, my original velocity, before I make any changes to it, is 8.5. My new velocity is still momentum over mass. But what's my momentum? Daniel, what's my momentum here? What's my new momentum, that is? Question number 2. Yeah, good. The new momentum is 4 times what it was. 4 times p. Okay? What's my new mass? Yep. 1/2 m. This is a little bit ugly, eh? If you don't like doing this the old-fashioned way, dividing fractions, really, I'd like it if you could divide fractions the old-fashioned way, but really that's not the point of physics. The point of physics is to be able to understand a problem, not so much the mathematics. So in the end, if you have to, do it on a calculator, if you have to. In the end, we really shouldn't have to here. 4 divided by 1/2 is what? 4 divided by 1/2 is the same as 4 times the reciprocal, right? 4 times 2 over 1. So what's 4 divided by 1/2? 8. Now we know what the value of p over m is. It's 8.5. So my new velocity is 8 times 8.5, which works out to be 68. And of course, the direction is the same as it was before. How many people got that one? Okay. You guys feel comfortable with the stuff that we've done here over the last couple of days? Comfortable enough to have our first quiz tomorrow? Let's do that. Okay, let's have a quiz tomorrow. It won't be crazy hard. Won't be any tricks to it. If you can do what we've done, let's say if you can do that worksheet and you can do these 2 problems here, you understand what we've done here. Doesn't mean you got them all right, but if you understand them all now after we've gone over them, you should be absolutely fine on the quiz tomorrow. You should get 100 on the quiz tomorrow. Okay? Yep. Did you? Did you get 3.09? I wonder if I typed that into my calculator wrong. Let's just check that again here. 8.25 was the original? Yeah. Yeah, I did too, actually, this time. I'm not sure where I got 3.28. I must have typed something wrong. So that's why, yeah, maybe. That's why nobody was raising their hand when, how many people got 3.09? That's better. Oh, I feel better about that now. Okay, so we'll have ourselves a little quiz on that stuff tomorrow, guys. We'll give you a little bit more practice here tonight just so that you can be ready for that quiz. We'll assign some check and reflect questions. And you might have a chance to work on those a little bit later on today as well. The check and reflect questions I want you to do are page 453, number 1 to 2, 5 to 9, 11, and 13 to 16. 1 to 2, 5 to 9, 11, and 13 to 16. So that's your homework for tonight. There will be no other homework tonight other than your quiz.